Good afternoon, everyone. Today, I'm going to introduce our research on Attosecond X-rays in the world window. Our Attosecond research is a continuation of the ultrafast laser research that happens since laser was first invented in 1960. As you may see from this graph, the laser pulse duration reached picosecond a few years after laser was first demonstrated. And then it reached to the so-called femtosecond in the 1980s. And the pulse duration did not change much from 1980 to 2000. Okay, that is because the pulse duration already reached the optical cycle or optical period of visible light, which is a few femtoseconds. That situation changed around year 2000. And the pulse duration has rapidly reduced to the attosecond. And 1 attosecond is 10 to the minus 18 seconds. The reason that people study ultrafast lasers is because these ultrafast lasers can serve as a fast camera to observe dynamics in molecules and atoms. As we all learn in fundamental physics, that electrons in the simplest atom, which is hydrogen, moves extremely fast. Both old quantum model says it takes about 150 attoseconds for an electron to orbit around the nucleus one cycle. Okay, pretty much like Earth is moving around the sun. And that time is faster than any camera that people has invented. So therefore, to take a picture, a movie of such a motion, you will need a time resolution of about 24 attoseconds. Actually, in atomic physics, this time is called 1 atomic unit of time. It's essentially the fundamental time unit to measure electron motions. In 2005, a theorist, Sideban, and his group predicted that if you remove electron from a simple atom, say krypton, or small molecules, say CO2, or complex molecules, it takes other electrons to respond in about 50 attoseconds. And he calls this time the universal atomic response time. And this is probably the fastest time scale we need to pay attention to when we study chemical reactions, like photovoltaic materials, and anything that involves molecules, for example. And apparently to resolve this kind of fast processes, we would need pulses shorter than 50 attoseconds. Well, it turns out producing attosecond pulses is extremely challenging. That is because the so-called uncertainty principle of Fourier transform says there is a connection between pulse duration and the spectrum bandwidth. To produce short pulse, you need a broad bandwidth. That is why very well known in electrodynamics, in optics, in any other field. And if you do a simple calculation, you will find out that to produce 25 attoseconds, you will need a spectrum that covers about 25 electron volts. That's extremely broad spectrum, and you cannot do this one in visible light. And if you just see the spectrum of this 25 attoseconds, it spans from 50 electron volts to 250 electron volts. And this is actually in a so-called soft X-ray wavelength range. The question is, how can you produce such a broad spectrum? And most importantly, how do you make all the frequency component that they oscillate in phase? Okay, so therefore they can add up constructively to make such a pulse. And people thought for a long time that it is impossible because most of the X-ray lasers, they have extremely narrow bandwidth. Therefore, they didn't know how actually to produce such pulses. And then in late 1980s, there was experimental discovery that says if you interact noble gases such as argon with intense femtosecond lasers, then you can actually frequency upshift an infrared laser to the X-ray wavelength range. And most importantly, the X-ray spectrum is flat, meaning that different frequencies has more or less similar intensities. And then, of course, people thought, well, if I can add up those frequencies together and control their phase properly, then I should be able to produce such a pulses. In other words, Attosecond pulse came from nonlinear interaction of intense short pulse lasers with gases. However, even though the spectrum was observed, but nobody was able to measure such a short pulses, and also the underlying physics was also not clear. Then in 1993, two theory groups explained the fundamental physics behind this so-called high-order harmonic generation process, this nonlinear laser atom interaction process. So what they are saying is the laser field that interact with this atom is so strong that the laser field itself is comparable to the internal Coulomb field of atoms that bond electrons to the nucleus. What happens is that the field can actually change the Coulomb well that traps electron to a Coulomb barrier. And we learned from quantum mechanics is that once you have a barrier, this electron can actually tunnel through this barrier and get freed. So once the electron is freed, this laser field can serve as an accelerator. In about 1 femtosecond, it can actually speed up this electron from 0 initial velocity to several hundreds electron volts, okay? And then this electron can actually recombine with the parent and emit actually photons. This whole process occurs within one laser cycle, within like femtosecond. And the emission and the recombination process is so fast that the emitted photon only lasts for attosecond, okay? And that's the process behind this frequency upshifting, and it's also physics behind this attosecond pulse generation. You can actually compare this kind of X-ray generation with conventional X-ray tubes, which everybody uses in hospitals. So in that case, you also free electron first from a cathode. In this case, you heat up this cathode and let it emit electrons. This process, however, is a random process. You cannot control when this electron is emitted. Unlike here, electron emission is controlled by laser field. And in hospital, you apply a high voltage between anode and cathode, and it accelerates electron to kilo EV or tens of kilo electron volts. And when this electron collide with anode, it emit X-rays. So there is certain similarity between this atomic process and a conventional X-ray tube. In both cases, you need a cathode. In this case, is an atom. You need a high voltage. In this case, is electric field. And you need anode. In this case, is again the atom itself. In this case, however, the electron motion, every step is controlled by external laser field. If I have millions of billions of atoms in this laser focus, and they all behave same way. So therefore, the emission from all these atoms will add up constructively and produce an attosecond pulse, where in conventional X-ray tubes, the radiation is random, so it's a long pulse. Well, this model also tells us that if you increase your driving laser wavelengths, you can actually control the photon energy or pulse duration of the attosecond X-rays. And it turns out that if you increase the laser wavelengths, you can produce harder X-ray or shorter pulses. That can actually be explained by Newton's mechanics. Essentially, when you increase your laser wavelengths, you increase the time that electron get accelerated. It's like whether you drop ball from a short tower or tall tower. Of course, in this case, electron will gain, or this ball will gain more kinetic energy. So in our group, we first used titanium sapphire laser, which has a central wavelength of 800 nanometer. And with this laser, we were able to produce X-rays up to 100 electron volts, and the pulse duration was 67 attosecond. Lately, everybody in our field has been trying to push the X-rays to the so-called water window, which is the photon energy between 280 eV and 530 electron volts. For that one, we need a higher long wavelength laser. This is a new laser we developed. This laser centered at 1.7 micron. It's a longer laser wave laser. And this is what it looks like in our lab. And with this laser, we were able to produce X-rays up to 500 electron volts. And in collaboration with Professor Zenghu Chang's group at University of Tokyo, we use this laser to study dynamics in NO molecules, and we were able to observe both electron motions and the nuclear motions. And the shortest pulse from this laser was 53 attoseconds. Well, here we are. We have now lasers working at 1.7 micron, but that's not the limit. At this moment, we are funded to explore new lasers centered at 2.5 micron and 4.1 micron. This should allow us to push the photon energy to 0.8 kilo electron volts or even above 1 kilo electron volts, and the pulse duration should be able to reach less than 25 attoseconds. Well, with that, I would like to summarize my talk. I show you that by moving the driving laser wavelengths, it is possible to produce shorter attosecond pulses with higher photon energy. Currently, we are able to produce water window X-rays that allow us to study lots of interesting physics and chemistry processes. And with that, I would thank our funding agency, National Science Foundation, Department of Defense. Thank you for your attention.